Okay, so let us now discuss the first introduction to AC analysis. We have to first start off with the concept of an AC signal. So AC compared to DC, it means alternating current, where we've been dealing with direct currents. So just to recap, DC stands for direct current. You have sources in which are fixed. So if you plug a battery in, this battery will connect to the system, and when you read the voltage out, you'll just get some kind of reading from it. So, this will be some kind of reading V out. And if we were to look at a curve of it, it would look like this. Doesn't matter whether you started to plug it in or whether you plugged it in now. If you kind of plug this battery in, it would retain a kind of linear, non moving curve that just stays fixed at a point, or that stays fixed at a level. Now we're going to talk about AC current, or AC signals. So AC stands for alternating current. The main idea is now, instead of having batteries, we have fields that fluctuate to generate some kind of signal. So you can think of it maybe like a signal generated from a coil. And this coil is configured in such a way that it allows us to generate a certain amount of power that's kind of peaks at some point, goes down, and then peaks at another point in reverse, or what we call alternating current. Compared to DC, AC fluctuates, but the term AC does not simply mean sinusoidal. It could mean any kind of signal that is periodic. So I don't have to use a sinusoidal, though sinusoidals tend to be the focus of circuit analysis. We could look at square waves. We could look at triangular waves, or sorry, sawtooth. We could look at triangular waves. And actually, all these signals are derived from an AC signal. In EE 3020, you'll hear this concept called a Fourier series, and we can use Fourier series to approximate a square wave, a sawtooth, and a triangular wave respectively, or any other kind of alternating wave with a measurable period as a sum of sinusoidals. That's the concept of Fourier. So in EE 3020, you'll hear the term Fourier series, which inscribes to you how to basically make these waves using uh, you know a bunch of sinusoidals. So that's the idea of alternating current. Now, historically, alternating current has kind of been tested as just ultimately superior, simply because by fluctuating the signal, you're able to deliver. You can wire it up in such a way called three phase that allows you to generate a lot of power. In EE 3300, you get to explore this concept a little further with three phase systems that look something like this, where these signals are basically 60 degrees out of phase with each other. And we'll explore the concept of what it means to be out of phase, lead, lag, and so on. So, in a three phase system, you kind of have something like this. And and they all connect to a common point called a neutral. Now, note, neutral, as the term describes, doesn't necessarily mean it's ground. Ground means 0 volts. Neutral means, measured 0 volts. So that's just the concept of AC. Now, a few other things before we kind of dive into AC is to talk about what's the symbol, what's the mathematics. So the AC symbol is looks like this. Now, unfortunately, we can't tell if this is a voltage source or a current source. So if we don't specify, usually the problem does specify, but if we don't specify, just assume we can say it's some kind of independent voltage or current source. And then we can extract maybe more information later on. Okay, so in terms of how to generate an AC signal, we usually have some kind of, say, voltage curve, which is equal to some maximum voltage that it can generate times the sine or cosine of some angular frequency plus some phase shift. And then if we want to complete it, we can maybe add an offset. So I'm going to call this V offset. This term tends to be ignored simply because it makes the mathematics a little more convoluted. And if we understand how to look at this signal as one way, then adding an offset just simply makes it easier if we understand the base first. So we're going to focus on this topic. Now, similarly, for current, we have Im, sine, cosine, omega t plus V offset. Now, in circuit analysis, the choice of using sine or cosine doesn't matter simply because sine of t is the same as cosine of. If we go through the math, we can say that if we asked, what is sine of 90 degrees? Using sine expansion, we can say that this is sine of t, cosine of 90 degrees, plus sine of 90 degrees, cosine of t. So sine of t plus 90 degrees is equal to, this becomes 0, and then we just have cosine of t. So notice that it doesn't really matter what you pick for sine or cosine, but to keep it consistent, usually we stick to one. And the one that we will stick to, and for the scope of this materials prep, we will focus on sine. And you can maybe adjust using this formula to find cosine. Okay, thank you.